So we're going to continue our discussion about structural systems. We've talked about the types of structural systems. We've talked about how important ductility is, but let's see how the building code actually uses some of this information and how we're going to use that information to come up with design loads. So let's use those structural systems and look at the building code and how it works with them. And we're going to use the 2018 International Building Code and its partner, the ASC 7, which was in 2016. Tables and codes define a lot of different building systems. Keep in mind the building code, it's not really intended for bridge design. The lectures are mostly focused on how we address building design. So I say there's three types of questions we need to ask ourselves to go into the code. First off is, will failure of the lateral system result in the loss of gravity load carrying members? Or in other words, if the lateral system is badly damaged, are we at risk of not being able to support the gravity loads? If the answer to that is yes, meaning we will lose gravity load carrying strength, then our structure must be in the bearing type of structure, often referred to as bearing wall systems, since most common systems use walls as the support of those gravity members. So for example, in a bearing wall system, if I have a shear wall on the side of the building, these beams are sitting on that shear wall. If that shear wall is removed, I've lost the support of those beams. Braced frames usually are not designed with the idea that the braces are resisting a significant amount of gravity load. But for some reason, if you did build a braced frame with a pin right in the middle of it, now suddenly if one of these braces is removed, the structure is going to become unstable. So these braces are bearing considered. Most engineers design their braced frame structures with the idea that the braces are not resisting the gravity load, even if they model it all as one unit. Now, moment frames, we should think about a little bit. Moment frames usually do have at least some gravity load sitting on them, such as these beams sitting on this moment frame. But if we switch those moment connections to pin connections, in reality, we still can support the gravity load. Now, we don't really lose connections during earthquakes, but we might run the risk of some of these rigid connections being cracked or damaged enough that they act as if they're pins, but we still should be able to support most of the gravity load, even if there's severe damage. So moment frames are not usually considered to be bearing systems. So we're still back on this first question. Are we a bearing wall system or not? If the answer to that is no, we are not, then the structure is going to be something other than a bearing wall system. The second question is going to be, which of the four types of structures are we using? Braced frames, moment frames, shear walls, cantilevered columns. Now, the building code does actually have another area that they refer to as dual systems, but dual systems are essentially just combinations of two of these four systems alone. The third question is, what's the level of detailing that the structure will be verified to contain? We haven't talked very much about detailing. We'll get into that more as we get deeper into the subject. But basically it's what are some of the items that are going to need to be checked by the engineer to verify that this structure should be able to behave in a ductile manner. The code actually provides 3 different categories. Ordinary essentially means that it's built with the traditional levels of standard engineering and construction. Doesn't mean that it's built poorly. It means that it's just built without a lot of specific detailing required for earthquake engineering. Ordinary detailing would be the way that the structure would have been built if it's in an area that has very low levels of earthquake threat. Special systems are those that have rather high levels of detailing. They're going to be able to minimize damage or really increase ductility significantly during a major earthquake. And intermediate systems are somewhere between those two. They have some of the requirements of a special system, but they don't have all of them. Now, it's important to keep in mind that the code is not saying one system is better or worse than the other. The code is essentially working with the idea that you can use any of these systems and get good performance in a future earthquake, but you need to follow the rules according to the system you're using. So what the building code contains is this table 12.2-1 from ASCE, which is what we're looking for is the R value. The R value comes from a table. This table is actually about 3 or 4 or 5 pages, depending upon the code you're looking at, but it basically gives us a numeric value that we're going to refer to as the R value of the structure. Now, the answer to question number 1 is going to tell us whether we're in this first A category or if we should be in one of the later categories. Now, I'm only showing a little bit of the table. I'm showing you a portion of A, portion of B. There's actually categories A through H in the actual building code. The answer to question 2 then allows us to narrow it down to we're using shear walls or for our structure or some other type of system. So if we're a bearing wall system, we're up here in A1, A2. If we're not a bearing wall shear wall, we're in categories B4, B5. Finally, the answer to question number 3 is going to narrow this down to a specific line in this table. If we want a concrete shear wall, bearing wall system, we can't have a special system. We can't have an ordinary. There is no option for intermediate. On the other hand, if we're building our shear walls out of masonry, there's actually 3 different options of ordinary, intermediate, or special. Some groups give us 2 options, some groups give us all 3. Trying to build a system that is not in this table is extremely challenging engineering-wise to get approval of what's to be built. There are methods in the code to go around that system, but it's usually a very expensive process, requires a lot of engineering, probably requires actual testing to verify that the system will work. So the R value is primarily based upon the expected ductility of a system. The code assigns this response modification coefficient based on, through experience, how we expect a system to behave ductile. A high R value indicates the building system is expected to remain ductile in a future major earthquake. High values of R would be 8. A low R value would be maybe 1.5. As you can see, this bearing wall system, special reinforced concrete shear walls, has an R value of 5. If you use an ordinary reinforced concrete shear wall, you get an R value of 4. So there are 3 questions to determine what structural system you're using. Is it a bearing system? Which type of lateral force system are you using? What's the level of detailing that you're going to conduct engineering-wise to verify that you can get a certain type of performance? Those 3 questions, you're going to locate the structural system from that table in the building code. You're going to look up the R value that is associated with it. Now, the intent of the code is not to define intent of the code is to define a design load that, if we use good engineering judgment, we use good construction practice, doesn't matter which type of system we use, we should get good performance in a future earthquake. Thank you.